starting today, just talking a little bit about how we keep structures safe after they are built and when they are in use. And that is what we call structural integrity management in many standards. And in this figure, that is the whole left-hand side, essentially. Of course, I'm pointing towards that you use managing structures in operation for the new ones, but you of course you continue to manage these structures also when they are in a life extension, and we will talk especially about that in this lecture. Someone is having the sound on, and that's okay if they have a question, but otherwise, please mute. So, yeah, general about structural integrity management, and then structural integrity management of aging structures or older structures, and something about how to manage non-physical aging. If you remember far back in the first or second lecture, we were talking about non-physical aging. And then asset integrity management is, of course, this is not something that only we structural engineers are doing. This is something that is done in electrical components, in anything, and then when you think of the whole building, the whole plant, the whole whatever, it's called asset integrity management. And I'll just give you some some thinking around that as well in the end. But we are interested in structures, I hope. So standards, they have sometimes rather peculiar and difficult language. So they say that structural integrity management is the ability of an asset to perform its required functions effectively and efficiently whilst protecting health, safety, and environment. And in my language, that is kind of, what needs to be done to keep the structures safe whilst in service. So that's trying to break it down to something more easy to read. And similar, this is, rather heavy English, but it's about, so when we know what we need to do, we need to manage those activities, things, people, contractors. Many times it's contractors because you have an inspector, an inspection contractor, etc. There's still one person that is not on mute and is making rather lots of noises on the line. Okay. So to keep the structure safe, we need to know what can go wrong and what's in the structure that is important in avoiding this. And we, of course, need to know the rules and regulation and what requirements there are to this. So back to at least one of you were obviously partying with my son a couple of weeks ago. But this is my son's drawings from some close to 20 years ago when he was trying to understand what I was doing. And it's a rather good drawings of what is bad for a structure. But if you get a very high wave offshore structure, if you get a high wave and hit it in the deck, that's bad. If you get some very heavy load for some reason from a wave, and if it's old, it's easily overloaded. And of course, also if it's damaged, as we talked about, damaged in the pile area. And then, of course, my favorite drawing when the earthquake. So, so yeah, so we need to do that, and so then we need to use the structure in accordance with its limitations. So if we found that there is a damage, we may have to say, well, you have to evacuate an offshore platform if it's going to be a storm. Or you may say that you're not allowed to use this bridge for anything, for any car heavier than 3.5 ton, etc., etc. So, and then you have to make sure that you actually are doing that. And then we need to detect changes, evaluate the significance, repair or mitigate if needed, and store all these data for further assessment. Especially when you get to life extension, you need all that data. And this is in many standards indicated by this loop, and then they might have a deviation into repair if needed, or things like that. And if things go wrong, we might also be responsible for having an emergency plan and emergency response. But that depends, of course, on what role we have. If we are the representative of the owner, we normally need to have, well, what do we do? What's the reactions that is needed if this building is starting to fall down? That is very well might be a part of us as structural engineers' responsibility. And in the end, you get figures like this. So this is the kind of getting the overview, understanding what is the limitation, the hazards, the regulation requirements, and everything like that. And then operate in accordance with the requirements and limitation. And then do the surveillance, do all the, get the data, evaluate the data, plan when do we look at things around the structure, and do the inspections or whatever it is. Assessment if needed. For example, it's needed when we do life extension often, and we repair compensating measure. It could be anything, but it often is repair. And then we have the emergency response. And I don't know how much you have had about management systems, but there is always this learning, trying to improve what you're doing and learn from what you've done good and what you've done bad and so on. So this is the evaluate and improve how you are doing this. So this is a typical management. This is more or less as it's written in some of the Norwegian standards. I think there is some small deviations to it, but more or less like it's written. In the offshore industry, the way we have been looking at structural integrity management, or making sure that structures are safe in operation, has changed over the years. Of course, as you probably know, here in Norway, we started up with some offshore industry in the early 70s, some discoveries in the 60s, but most of the activity started in 70s. And but in US, they had a lot of platforms much earlier than that. And then I kind of indicated the big accidents through the history that really has influenced the structural requirements. So this is the early hurricane damage in the 60s with Hilda, Camille, and in UK there was a sea jam accident that also influenced us quite a lot in Norway. This is Alexander Kielland, the Norwegian accident, Piper Alpha, and then you had a hurricane, Andrew, in US, and then you had Ivan, Rita, and Katrina in US, and Deepwater Horizon. And many of these, I guess, you heard about. But for example, so we were doing what we call a calendar-based inspection program, and we are doing that in many industries still. But in shipping industry, they have this that you need to get into dock every so and so often, maybe a fifth year, for example, and go through, inspect everything in that ship, and get the certification from a society like DNVGL or Lloyd's Register or something. This ship looks fit for 5 more years. And that's that kind of calendar-based inspection, that planning, that was used also in in the offshore industry in the early years. And then then in the late 80s, maybe early 90s, we became quite a lot better in understanding risk-based inspection. And here we had this that you now know is old-fashioned and a little bit peculiar way of defining risk. That risk is equal to probability times consequence. The funny thing about that was, of course, a lot of the calculations they did was a very high consequence thing if it had zero probability of failure in that calculation. How many inspections do you do? 0. And that's not what we are doing with our probability models. You know now, but a lot of errors was done in this area in the early years. And then we got into a lot of these Ivan, Rita, Katrina accidents, and this more a SIM regime got more attention, and that is, well, it's not just inspecting whether it's cracks or corrosion on this structure. We have to look at the whole, everything that has to do with the safety of the structure. If we just keep looking and inspecting to find cracks, but the loads are changing dramatically, like they were doing in Gulf of Mexico, well, we're not doing our job properly. So, and then, well, that means we need to look at everything that has impact on the safety of structures. And we are not fully there yet, but we're getting there. So standards have similarly been updated in the early years of offshore industry, where we were using DNV in service inspection methods. Then this was transferred to the governmental agency, NPD, for many years, and then it was transferred again to an industry standard called NORSOC N005, which is we should have. You have access, I guess, to many standards that I don't have, but I think I can upload a older version of this at least. And then in around 2012, 13, 14 or something, there was an attempt of making this into a SIM standard. In my opinion, didn't fully succeed, but getting closer. And then there's also ISO and API standards going on at the same time. Similarly, for land-based structures, I'm sure, but I'm not that familiar with that. Okay, so this is so now we go through this four parts process and look a little bit on what they are. So the first one is data. So essentially, we want to have all the data that we need for a structure, so we can at all times propose the cheapest often, but also the best repair solution if it is needed. And we need to have the data so that we can say, well, you need to repair or you don't need to repair, because that's got to be quite a big difference in money for the owner. If we have been bad at keeping track of all data, that could be expensive for the owner. If the owner himself have thrown away all the data, that's another problem. But and in your projects, you will see we have always insufficient data. So, but normally we want a little bit on generic information. Who's the owner? What's the size? What's the drawings? Everything like that. Want information about the design regime, condition, configuration, loads, and so on. A little bit like what we had. We can also say it like this. Well, we want to know how it was built, and then we want to know all the changes that has happened to this structure after. Changes that has been implemented in use, changes around knowledge, changes in requirements, changes in loads, changes in condition and configuration. If we know all these, if we know how it was built, everything about how it was built, all the changes, then we know how it is. So that's essentially a way of illustrating what we want to achieve. And here's, of course, one rather, you can say, a little bit advanced. It's in the presentation, so you can maybe study it a little bit more. But here you start with, say this is your big database on your computer. You have all the generic information, owner, size, and so on. And then you have all the as-built information about the design regime, regulation, standards, specification, procedures, about the condition, material properties, dimensions, coating, the configuration, how the layout and geometry, permanent weight, position, water depth, and orientation, and on the loads, design and operating method and accidental. Here it's offshore. I used a little bit of offshore terms, but this you can transfer to land-based structure easily. And then you want to know, well, what kind of surveillance program has been implemented over the years? And that's, of course, here it's a kind of compliance management. Have the standards changed? Are we still in accordance with the standards? For the condition, it's of course inspection, mitigation, and modification. And that's for configuration as well. And for loads, it's maybe load monitoring, but you find something from inspection as well there. For example, on an offshore structure, if the marine growth has become extensive, then the loads will have changed. And then in service changes around the design regime, we will need to have a register of all regulatory changes, the standard changes, and an updated design specification if the owner makes things like that. And in the condition, we want to have a register of all inspection data, structural repairs that we have performed, modifications, monitoring data, and accidental events that has occurred and been registered. And here, similar for changes to configuration and similar for changes to loads. And then you put all this into a database that you call a change register. So everything, all the changes to keep up with this, you know how it was, and have an overview of all the changes. So you put all these changes into a register, and then you take the most important of them into your computer analysis. And you redo your analysis of the structure with those. But you need to have that registered because maybe you were not doing all, you were not including all the later you see, oh, this is more important than I thought. So you need to keep that register. These are the ones I have, and these are the ones that are kept in the analysis. That's at least one way of organizing this, making sure that you know all the changes you have and implementing those into the analysis. The next step is evaluation. And of course, I'm talking a little bit overlapping here, but so when surveillance and inspection and monitoring has detected damage or anomalies, we need to decide whether repair or mitigation is needed, or if the structure can be left as it is. This is very much what you are doing this year for the project. Most of you, at least. And repair and mitigation are costly, and actually sometimes when you repair a structure, you're not necessarily just making it better, you may also introduce new problems. So you don't want, you have to want to be critical about the repair you are doing. So you don't introduce weaknesses and you don't do anything that is overly costly. So you want to do some so-called evaluation, and this is the figure that I made for around this. You have the survey data, you have a trigger that you have a damage or anomaly, and then you do the evaluation. Is the damage or anomaly significant? And often that's a local check if the component has sufficient strength and fatigue life with the damage or anomaly. And in some standards they say, well, if the loss in strength is less than 10% due to the anomaly, then it's regarded as insignificant. But that's not always correct, is it? If you are doing your design of a steel beam, you will, I guess, often try to have the utilization to be like 0.999. Will that be your ideal? So when you check when you do the code check, will 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 you optimize or will you leave some extra strength in? A lot of you will optimize and say, well, if the concrete beam, I can reduce the number of reinforcement bars because it's and sometimes people are calling it overly conservative. So 10% is not, if the beam is very optimized, 10% may be too much. And then if this fails, we go into assessment, and that's coming later. And that's more analysis and things like that. Surveillance is the ongoing activity to gather information about changes and so on. Of course, I'm calling it surveillance because I don't want to use the word inspection, because you do more than inspection. You do document review, you read through new standards, you check if you are in accordance with these new standards, you do stuff to find out load changes as well. But I will probably do the mistake many times and say inspection rather than surveillance, but that's the idea. And so what we do for aging structures, how does this regime of taking care of structures in operation change when we get an aging structure? In the design life, we do not really expect failures. I mean, when we buy a new car, we expect the car to be more or less functioning for how many years? 10? And then we kind of think, well, okay, after some maybe 8 years or something, okay, then we start to see that things are starting to go wrong, and we need some repairs and changing things and so on. But essentially, and that's also with structures. We essentially we don't expect things to fail very much, except of course the odd occurrence of that anybody did an error in design or fabrication, or if there was an accidental event. In life extension, in contrast, we have to expect that failure occurs, and we have to expect that structures no longer meet the requirements. This is a little bit difficult presentation, but it has many structures simulated through the life with in a probabilistic sense. So here you see this is 1, 2, 3, 4, 5, 6 structures simulated more or less with the same model. This one this has is getting an increasing load all the time. So you see that is really getting up to high failure probabilities at an rather early stage, but these are mostly just, we are just looking at fatigue cracking on these. They had 20 years design life, and as you see, after 40 years, some of these structures start to deviate, and that's because the inspection on these and repair regime on these was modeled in a computer not as good as these three. And what conclusion we can draw from this is that here we are inspecting. Some of them we are not inspecting at all. Some of them we are inspecting in a bad manner, and some in a good manner. But it doesn't change anything on the probability of failure. So that's my conclusion to that, is that inspection in this period is more or less just an insurance. We want to check that it's okay. We expect it to be okay. We want to check that it's okay. And we are told, yes, it's okay. Hopefully, in most cases. When you get out in the life extension, then the safety directly is dependent on the regime that you are doing inspection and repairs. Then there is a big difference on what you are doing. This difference can start earlier, or if it's dramatic changes like this load change that happened on this, or it can start a little bit later if it's more minor changes like fatigue that happen to this one. So, but that's a little bit of the story that we have. And okay, so this is a theoretical thing. What's happening in reality? And this is for offshore, so some offshore structures. And here I normalized and so on, so you don't get to know how many cracks that is in this database, but for some of these platforms, it has been up to 250 cracks a year. But you see very clearly that there is a trend towards getting more cracks with time, with age. So that's, yeah. So and then we have talked a lot about the physical changes now. So we need to do a little bit. We have to recognize all types of aging changes, and we just repeating for you. We talked about this as physical aging, technological aging, structural information changes, and knowledge and requirement changes. And knowing the condition of the structure, we need to have the history of degradation, damage, and changes. We need to know the present condition. This is, of course, yeah. And of course, we need to keep these data. So if we lose any of these data, we have less reason for believing in our structure, and that means there are more uncertainties. And as you know, if we are to model that in a probabilistic or risk-based thing, having uncertainty increases our probabilities or risk. So we need the SIM strategy needs to include managing the approach to assess aging processes, need to link surveillance requirements to aging processes. The surveillance program need to more detailed surveillance may be required if life extension is to be justified. As you saw, it depends on the inspection regime or surveillance regime that you are using. The evaluation needs to include the gap between original design requirements and current requirements, need to cope with possible widespread degradation and damage, and the information management need to deal with old file and filing system and possible lost data. Many times when you are to be, if you are to do analysis of an aging structure, you will be told that it's, I think all those data, they are in a storage, and they have to think hard where that storage is, and it's far away. And then you, even sometimes you will say, but I think it burned down. So I experienced that at least. The non-physical aging. So technological changes, obsolescence, spare parts, and compatibility. For obsolescence, there are actually standards and spare parts and so on. So if you, for those that are more mechanical engineers and with machinery and so on, how to manage spare parts, compatibility, and obsolescence are actually to some extent described in standards, and that's quite important for structural engineers. Obsolescence is maybe not the most problematic type of because we don't have the same need for spare parts and so on. But of course, it might be problematic if we need to do repairs on something that is welded with an old technology and with old steel, and we are introducing new steel. You could have these kind of compatibility problems if the quality of these are so that the old structure starts corroding heavily because of the difference in materials and so on. So it's not irrelevant, but it's often not as much a problem for structural engineers as it is for mechanical engineers. Structural information changes that we talked about, the storehouse that I discovered that was burned down, knowledge, monitor safety notice, reports, accident investigation, papers, and other research. And that's why we essentially have libraries in many companies. And changes to requirements, very much the same. That is something we hope that we can do with libraries and documentation and so on. So this is the core of the kind of a little bit of introduction. Now we will next in the next lecture we will talk about more about the inspection method to get more into the details. But this was trying to give you the overview of what's the process. So now you know we need to know what is problematic, what is the hazard for our structure, how can it go wrong, and then based on a very good mapping of everything around that and what the regulation requires, we can start to make how is it okay to operate this, and then how should we inspect, how often should we inspect, how do we store all the data about those inspection and all other data, and how do we evaluate and assess, which means analysis. And of course, if we found something that is very bad, we need to do some mitigation or repairs. And of course, historical maintenance, the condition have been the issue. Later in SIM, it's more about the whole everything that influences the safety of the structures. And aging structures are expected to have experienced more damage and deterioration, and SIM activities need to be intensified and inspection intervals reduced.